A search service on a 4 GB container kept OOM-killing itself every 30 minutes under moderate load. The team assumed a memory leak, but the real culprit was an in-memory HashMap storing unsorted postings lists for 10 million documents, causing OOM intersection and memory explosion. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover inverted index and text search. An inverted index is a data structure that maps each unique word to the list of documents containing it. Instead of scanning every row with a like query, you look up the word's postings list and get results instantly. Think of a cookbook index. You look up chicken and get page numbers directly. Every time you write where text like %search%, the database scans every row, that's O(n) per query. With an inverted index, you precompute the word-to-document mapping, making search O(1) per term plus intersection cost. For read-heavy workloads, it's the only sane choice. Building an inverted index involves 3 steps. Tokenize each document into words, map each unique token to a list of document IDs, and then sort each postings list. Sorting is critical for efficient intersection later. Here's a simple Java implementation. We iterate over documents, split on non-word characters, lowercase, and add each token to the index. After building, we sort each postings list. The output shows tokens mapped to sorted document IDs. Tokenization is how you split text into tokens. A classic rookie mistake is splitting on whitespace only, which leaves punctuation attached. Always lowercase and split on non-word characters. For production, consider stemming and stop word removal, but be careful. Removing not can flip meaning in legal documents. Here's a tokenizer that uses a regex pattern to match word characters, lowercases, and removes common stop words. The output shows clean tokens without punctuation or filler words. Given 2 query terms, you need documents containing both. With sorted postings lists, use a 2-pointer merge. This is O(n) plus m per pair. For large indexes, skip pointers can reduce comparisons further. This is the classic 2-pointer intersection. We advance pointers based on comparison. For very long lists, add skip pointers at intervals to skip over blocks that can't match. Phrase queries like quick brown fox require documents where the terms appear consecutively in order. To support this, store term positions in the postings list. Then check if positions of consecutive terms differ by 1. This positional index stores a map from token to a map of docid to list of positions. The phrase query checks that positions of consecutive terms differ by 1. Note, storing positions as list integer per doc can be memory heavy. Use primitive arrays or compressed bitmaps in production. For millions of documents, an in-memory HashMap won't fit. Use disk-based indexes with block compression. Common approach: store index in multiple segments and merge periodically. Use memory-mapped files for fast access. Here's a simple disk-based index using random access file. We write term length, term bytes, postings count, and postings. For production, always call channel, force, true after writing to ensure data is on disk. Inverted indexes are great for keyword search, but terrible for fuzzy search, regex, or numerical range queries. For substring matching, use a trie. For geospatial, use an arttree. For small datasets under 10K documents, a simple scan might be faster due to index overhead. This is the same issue we highlighted at the start. Here's exactly why that happened. The team built the inverted index in memory as a HashMap string, list integer for 10 million documents. The postings lists were unsorted, so intersection required ON*M scanning. Memory usage exploded because each postings list was stored as an array list with overhead, leading to OOM-kills. The fix was to switch to sorted postings lists stored as int arrays on disk with memory-mapped files. Intersection uses binary search. Memory dropped to 500 MB. The key change was sorting postings lists after building, enabling efficient merge-join intersection. This is the exact line that caused the OOM incident. Storing postings as unsorted array lists in a HashMap for millions of documents leads to memory explosion and slow intersection. Always sort postings lists and consider disk-based storage for large indexes. If you forget to sort postings lists, intersection becomes ON*M instead of ON plus M. Always sort after building. This is a common production trap. Storing positions as list integer for each document creates huge memory overhead. Use primitive int arrays or compressed bitmaps like roaring bitmaps for production. Always call channel, force, true after writing to ensure data is on disk. Otherwise, a crash can corrupt the index. I've seen this lose hours of indexing work. The article mentions skip pointers but doesn't show code. Here's a concrete implementation. Store skip pointers at intervals, e.g., every sqrt, n entries to skip over blocks that can't match during intersection, reducing comparisons from ON plus M to O sqrt n plus sqrt m in practice. The article mentions ranking and passing, but doesn't implement it. Add TF-IDF scoring to rank results by relevance. Term frequency, TF, in document multiplied by inverse document frequency, IDF. This boosts rare terms and penalizes common ones, improving search quality significantly. The article's FAQ mentions copy on write for concurrent updates, but doesn't show code. Here's a minimal implementation. Build a new segment in memory, then atomically swap the segment list. Queries see the old segments until swap completes, ensuring consistency without locks. When search returns no results for a term that should exist, first check tokenization. Run your document text through the tokenizer and verify the term appears. Check case normalization and stop word removal. Use the Index Inspector tool to inspect the index. Let's run through some common interview questions. How does an inverted index handle concurrent updates? Use copy on write. Build new segment, atomically swap. When would you choose inverted index over B-tree? For full text search with multiple terms and ranking. What happens when a term appears in 90% of documents? Postings list huge. Mitigate by skipping high-frequency terms. And a few frequently asked questions. What is an inverted index? Maps each word to list of documents containing it. How to implement one? Use HashMap string, list integer, tokenize, sort postings. How does Elasticsearch use it? Per shard, with segment merging and memory mapped files. To recap, inverted indexes turn ON text search into O1 term lookup. Always sort postings lists after building. Tokenization is the most common source of search bugs. For large indexes, use disk-based storage with memory-mapped files. Ready to go deeper? Up next, backpressure, then transactional outbox pattern. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.